So we'll start now. Started the recording. So uh, just to remind us, this course is on antenna design and simulation with MATLAB. And the previous class and first class, I had uh, introduced everyone to this course. So we'll skip all this. Oops, I'm sorry. Okay. Regarding file sharing, so I have again shared the files in the group today. Yes, uh, 10-15 minutes ago, I had shared all the scripts that we plan to run today and the lecture 3 slides, which is this is the lecture 3. And I had also shared the recordings of the first lecture and the second lecture. So I think all the material is up to date in the group. If you had joined the group late or you have not, like you don't have access to these materials, do post a message in the group. I'll share them again. And so today, I think I'll be just giving out assignments or homeworks verbally. I have not mentioned them in the slides, but previous lectures, there were some assignments. And I hope everybody is in the group. If not, do reach out to me if you are joining through the Teams link sent via the email and you have not joined the WhatsApp group. So this lecture will start with antenna arrays, but before we do that, let me quickly check if the patch antenna code has run. So I had shared this patch antenna code with everybody. Uh, where we design patch antenna in yesterday. Yeah, in the last class yesterday, we quickly went through the code and uh, all the aspects. Let me just uh, discuss the what this is. The results to this side. These are the results which I did not run show yesterday by running the code because this code takes uh, 10 minutes, 15 minutes around to run. Okay, so the code, like the previous codes, we have we first define the environment and things. These are not necessary. Then we assign the antenna parameters. We created the patch instance by using the patch microstrip class of the antenna toolbox, and we gave the design frequency as F naught. So this will create a patch automatically at this particular design frequency. But again, we'll have to correct the effective length, and then we modify the substrate of the patch instance by using stylic trick, and then the library yeah, we can also directly yeah, you can use this instance. You can define the substrate name, the epsilon r, and the loss tangent, and all this will by default assign these values. And then we modify the patch length and width based on the effective epsilon or the in this epsilon r of the uh, FR4, and then we change the patch length by using a small downward shift. And then we change the ground plane length as well. So we created the patch at this frequency, but we then modified it a little bit to suit to get a but better resonance. But and then we use the show patch function to see the patch. Let me quickly open the patch. So this is how it will look like. If you work in MATLAB online, while writing the code, all these simulated results, they collapse, and then you can open each of them individually and look at the results. So this is how the patch now looks, and then you can zoom in to see the feed location, which is somewhere here. Here is the feed. We can also rotate this and see. See, you can see the field location here. Right, so this is the field location, and since we have a substrate over here, so it's harder to see the field throughout this, but you can uh, remove the substrate and then look at the design as well. There's also you can also do a feed microstrip. I'll leave that as an assignment to you. And the codes are available if you just Google them. And also there is the MATLAB antenna toolbox website where you can go and check the different antenna examples that are there. So yeah, so we look at the geometry and then we can do the frequency analysis, similar to the previous one, which we give a start frequency, end frequency, and the number of points, and we use linspace to create a vector. And then we give this the number of the frequencies at which we want to simulate, the Z naught value, and the instance of the antenna that we want to create. In the previous examples, like loop, monopole, dipole, we used to name these instances using and, but it's up to you. You can use any name for the instance that you create. So for patch, we have written patch, and then by using the S parameters function, we'll get the S parameters. Like earlier, we'll squeeze the S parameters, get the S11 magnitude, and then we'll plot it. And if we can look at the this was the geometry, and then yeah, this is the reflection coefficient plot. So this is the S11 plot. As you can see, the resonance is at 9.7 gigahertz. Um, are there any questions? If there are questions, you can type in the chat or raise your hand. I'll come to you. So this is the reflection coefficient of the patch. It is resonating somewhere around 9.7. Um, you can look at the input impedance Smith chart as well. And again, this will show us that it is somewhere around 9.6 gigahertz, some close to something like that. So, and again, this um, I've not plotted the input impedance plot, but like the previous examples, you should include the input impedance plot as well and see uh, where it cuts the real axis. It's the same information you can get it from the Smith chart as well. So it is cutting it over here somewhere between 9.6. So the resonance is here. But it's not tuned because we wanted to resonate at 10 gigahertz. And the reason why I shifted the frequency to 10 gigahertz is because an antenna at 2.45 gigahertz, a simple microstrip patch, is a little big, and then bigger structures take longer to simulate. So I shifted it to 10 gigahertz, and similarly, I'll show you the script for the horn antenna. And horn antenna is even bigger. So to resonate at 10, it will be still be pretty big. So so to demonstrate and also to show a use case, we will simulate the horn antenna at 77 gigahertz, which is the automotive radar band. And like the previous codes, we again we solve. These are the same functions. Like you can copy paste from each other. scripts as well. So once you have the antenna element, you can get the S parameters, plot the S parameters, plot the radiation pattern. The pat the pattern function is pretty simple and straightforward. You name the antenna instance and the frequency where you want the pattern. It will create the pattern. Similarly for the radiation pattern cuts, as you can use pattern azimuth, pattern elevation, and give the antenna element, the frequency, and the for azimuth you will have to provide the uh, phi value, and then for elevation you will have to again provide the theta value. Similarly, you can get the gain from the pattern and efficiency from the pattern. Um, so it's all the same things that we've been doing. And then you can also again plot the current distribution, use the current function, and this I've also given a script to find out the peak gain, but you have to make sure you use the correct direction in which the peak gain is. So that's not tuned over here. So the peak gain will not be good from if you run this script. So you'll have to find out the correct angles when you need to look at to get the gain. So okay, let's look at the surface current plots. So here is the surface current plot on the patch antenna. Similarly, you can and also you can plot all the sum gain all the patch antenna summary. So you can see we the intended design frequency was 10 gigahertz. The resonance is at a different frequency. So this has to be tuned. Once you tune this and choose the correct angle, the peak gain will also improve. Radiation efficiency is bad because the antenna is not matched, and rest is the the physical parameters of the patch antenna. So this was we discussed briefly the things on the patch antenna, and then we sorry about that. Yeah, give me a second. Um, so we were discussing the patch antenna design, and we've looked at the results. So so I'll show the horn antenna script now, and then we'll move to the antenna arrays. And if there are questions regarding this patch antenna and the horn antenna, I'll pause, and or maybe you can ask while we discuss. Okay, so this is the script for the horn antenna. I've not prepared slides on the horn antenna because I think you can follow the script now, given that we have seen scripts for and slides for monopole, dipole, loop, and slot. So it's in the similar lines. And now we'll be just changing the class function which is being used to create the antenna. So like the previous scripts, we set the plot styles and the clear, close, and CLC. So these are not important, but it makes the script the results look better. And now we again define the frequency parameters for the antenna. The like the previous slide, the previous script. Now, to create a horn antenna, we use the class horn, and we give a frequency f naught. And if you if by and what this does is this creates a horn antenna automatically at f naught for at starting with f naught frequency for f naught frequency resonance, and we create an instance and for this horn. So make sure you don't use horn over here because then that will clash. You can use horn 1, horn 2, or horn 77, something like that, and that would work. And then once you've created the horn, so by default it creates it uses metal as PEC. You can change the conductor as conduct as the the instance name dot the conductor, and then the conductor has again property as name. So and then you can choose copper, and then you can define the conductivity and thickness as well. So if you look at the ant instance, let's open this. So if you go to the workspace, they should yeah, they should open your the horn on structure on the object. And then the object has these properties. You can see the flare length, flare width. So these are all calculated automatically based on the frequency that you shared. So this will become flare length, flare width. So this all will be defined, and then there will be length, width, and the feed location. You can and if you need to modify, what you need to do is you will write horn dot feed location and then equals, and then define this like a variable, like the position that you want to edit. So all these attributes you can change and see how the antenna changes, the antenna element changes. So this is how this looks. And if you once you have set all the design parameters, what you can do is you can use the show property again to see the antenna. In between, if you go through the script, so I've included some calculations based on textbooks that like the gain that you expect from theory, and then in DBI, and in this particular script I've included a lot of print functions so that whatever is simulating or whatever the properties are, you can all see it in the command window. So it will print these things as well. So the print functions just print whatever the values that you want. They are not necessary to this code. You can always go to your workspace and look at the values, and these values you can select to whatever value that you want to print. It's just to make it convenient to look at whatever values that you quickly want to see in the print function. Also, print function is pretty useful while debugging the code. So you can include prints here and there, and then if the code stops at any place, you would know up to which point the code was the code worked properly. Okay, so you can use the geometry, and once you use the geometry, it will show you the antenna, the horn antenna, and the horn antenna automatically generated one looks something like this. Um, You can see, and it has generated horn antenna, and the feed location is somewhere here. You can move the feed back and forth and see how it affects the impedance match. And if you look from the inside, you'll see what is a good angle to see. Yeah, you can see this stub over here. So this is how the horn is being fed. So it has a pin inside, and its length essentially will also tune the impedance matching. Your matching over here. So, but if you design the horn antenna automatically, it will be all matched and correct. You might want to tune it a little bit, but make sure while if you're practicing this thing, you run it at a very high frequency, because if you do it at a lower frequency, it takes a while to um, simulate. So this takes. I'll run this again for you. Let's see how much time it takes. It should take like 2, 3, at best 2 minutes or something. Yeah. So sorry, it shows 51 over here, but I've changed it to run it only for 21. Oh, sorry, just 11 points. So for 11 frequency points, uh, this takes around like 10, 15 seconds. And then it will take some time to generate rest of the results. Meanwhile, if there are questions from batch or previous classes, um, please do ask or write it in the group. Yeah, so this takes a while to get the results, but it should not be too long. It shows simulation complete over here if you notice. Yep. We have all the results now. So if you go through the script, you'll find there is a portion which plots the performance summary, and it will show you the center frequency, the conductor, flare length, and everything by creating a table, and then we use a UI to plot these values. So you can go through these parameters, and if you tune it, you can achieve even better performance. So this is the performance summary over here. And then if you plot the surface current, this is so the antenna on the horn antenna does not have high surface current distribution. But if you look inside, yeah, then you would see the feed over here. So you can see this has a high current distribution, and then you can zoom in also and then see. The current is zero at the top, so it this behaves like a dipole, which is exciting this waveguide, and then this waveguide it flares up to match it to the air. So you can go in detail of how an antenna radiates, but you can see so the current distribution plot shows that we have high current on at the feed port. Looking at the gain, so this is typical for a horn antenna. The gain is usually around 15-16 dB in this frequency. At this particular frequency, if you tune it, this will go up to 16 definitely. And then looking at the E and H plane radiation patterns. So this is the E plane cut. This is the H plane cut. So all these can be created by the pattern function. And here is the radiation pattern, 3D radiation pattern. So you can see if you can also rotate this thing and see. So the antenna is radiating in the direction of the flare. Also notice that the horn is rotating over here also. This is your if you look from the top, your this is your H plane, and if you look from the side, this is your E plane. So this matches the E plane pattern. So this is the 3D radiation pattern. And then if you look at the Smith chart, you'll notice that this this is although this is cutting close to so this resonance is somewhere here, but in this case the entire the S11 in the Smith chart is very close to 1. So this shows that the antenna is actually pretty well matched. This is very close to 50 ohms, and this is reflected in the S parameters as well. So if you compare the Smith chart to your S parameters over here, let me make this small. Mm. Also the input impedance flow. So this is your S parameters. This is a Smith chart and the input impedance. So if you notice, your S11 is completely below -10. It's close to -20 dB. So this means this is pretty well matched. This is also reflected over here. So your imaginary part is close to zero, although it is increasing, but your real part is also close to 50. So this shows the matching is very good from the waveguide to the flaring and the dipole, and your so hence it's radiating pretty well. And you also we did see we looked at the gain plot, and the gain is also very good at all close to 15 dBi for the entire frequency range. So this is the script for the horn, and quickly going through the script you'll see. We have again we're using show antenna for geometry, S parameters from S parameters function, uh, and then these are all for plotting. We are calculating the input impedance from the S11 by using the same formula that we used in the previous codes. Smith chart again by just using Smith plot pattern, 3D pattern from the pattern function, giving it the antenna object and the frequency where we want to see the radiation pattern. Then azimuth and elevation plane from the pattern azimuth and pattern elevation. Then the script to get the gain values from the horn antenna. And in the case of horn antenna, we know that the maximum radiation will be at EZ equal to zero and uh, AZ equal to zero. So at 0, 0, that is in this direction, we have the maximum radiation. So we just put the angles for azimuth and elevation as 0, 0, and you can get it. We at that particular direction, we just keep saving the gain values, and then we plot this. Similarly, you can calculate the half power bandwidth by just uh, like getting the elevation pattern and then calculating the half power and say and then printing it. So you can go through these this the script line by line, and this should help. And similarly, for surface current, you just use the current function and then calculate the bandwidth, and then plot the performance summary. So this is the horn antenna, and we have also discussed the patch antenna. So that's all, I guess, for the antenna designs. We won't be covering any more antennas. Next, we'll start with antenna arrays. We'll do linear dipole antennas today for broadside and end fire radiation, and then tilting the beam or phased array for beams steering. Um, And yeah, so that's all we'll cover today. And maybe and tomorrow, not tomorrow, in the next class, we'll look at maybe 2D arrays and then finally the UI designer app. Are there questions regarding the patch antenna or horn antenna? Meanwhile, I'll just show you and send the link to the examples that you can look at from the MATLAB's own repository. So this is the website, and I'll paste the link here in the Teams chat and also send it to the WhatsApp group. You can navigate around this website and you'll see several examples. So here are many examples like a double slot cavity patch on a TMM10 substrate, so like PCB for USB dongle. So there are different toolboxes, and let's open the antenna modeling analysis. See, you can design a spiral antenna, and the script is given over here. So if you can open this in MATLAB online, it's click on this. You have access to MATLAB online. Continue in this window. See this So it's not working perfectly. Let me uh, essentially you are able to open the script and we use close it. Too many windows are open. There is something happening here. Essentially, you should be able to run scripts from here. Yeah. So once you open the example, you can run the script using this, and then they should run that particular example, and you can analyze. So you have to note that this, if you look at these lines, so these are the active scripts script card, and then MATLAB has somehow put very beautiful uh, comments over here too. This when this runs completely, it will uh, shows all the plots that are intended for this. So let it run. We'll start with antenna arrays. So this was just to show you. You can go to the this particular link and then uh, check out which examples are there, and then um, you can do a lot of things. See, there is example how to calculate the axial ratio and reflection coefficient, and all these things you can actually plot. So I've not shown you several functions like return loss, PSWR, charge, current, mesh. You can also use mesh to see the mesh. So there are several functions which you can actually check out from the toolbox. So we'll start with antenna arrays, linear arrays for which we intend to cover today. And we won't be getting into the theoretical aspect. What we need to do is we need to focus on how to run the script and the effects that we need to see. So, if you recall from the antenna lectures, we studied antenna arrays, and over there was this term called array factor, which is essentially which you multiply uh, with the element pattern. So array, uh, your array factor and your element pattern, when they multiply, you get the pattern for the antenna array. So that's what we'll see. And then we'll see three cases. The first is for broadside, which is the best example to learn the script. And then we'll look at the end fire and then phased. So we'll start with a broadside array, and a broadside array looks like something like this. So we'll see the script for this, where we have the dipole array. looks something like this. And if you look at from the top, you'll see you have the dipole arrays lined up something like this. So there are eight of these, six, seven, and eight. And from the top, the radiation pattern would look, and these are all in the x-axis and the dipole. So this is the x-axis. This is the z-axis. So the dipoles are all in the z-axis and they're lined up in the x-axis. They're separated by some distance d, and all of them are in the same phase. So all of them are at 0 degree phase. There is no phase shift between them. And then they're separated and they're excited with the same amplitude. Okay, all of them have the same amplitude. And in that case, sorry about that. And in that case, your antenna pattern looks something like this. So, and this is this direction, your since your array is aligned like this, and the radiation is in the in the axis normal to the array. So this is known as the broadside array. And if your array was aligned like this and your radiation was in this direction, because this is towards the end of the array, this would be end fire. The broadside is normal to the array axis, and end fire is in the direction of the dipole array. So if you look at the orientation of the array over here, the array is lined up like this, and your radiation is perpendicular to the perpendicular to the array. Okay. So the motivation, why do we need arrays? If you use a single dipole, because we're taking example of dipole over here, but it could be any single element also. It would generally have a lower gain. I mean, sure, horn has a gain of close to 16 dB. But if you make an array of a horn, then its gain will also increase. And then the beam width is very wide. If you compare the for a dipole, the if the radiation, sorry, for a dipole, we change the, yeah, for a dipole which is aligned like this, its radiation pattern looks something like this, right? But if you make an array for several dipoles like this, its radiation pattern will become much narrower, right? So you can achieve a higher, narrower beam width and a higher gain. And in dipoles, you cannot have any beam control. You cannot tilt the beam in different directions. But if you used an array and then you give different phases to the each element and change the amplitude of each element, this would also allow beam control and steering capability. And for and we want we generally in antenna design we prefer a higher gain, a narrower beam width, and a controlled radiation direction, which is again you can use phase array and then beam steering, that you can keep changing the phase and you can keep scanning. For example, if you introduce several elements over here and then if you keep changing the phase of these elements, you can change keep tilting the beam in different direction to do scanning. So that's how the phased array works, and that is a logical step. But before that, we must learn how to do design normal regular arrays, and then we can do a phased array. So what is an array? An array is a collection of radiating elements. So which are arranged in space with controlled spacing, amplitude, and phase. So each of these element will be receiving excitation, right? So each dipole receives an excitation A1, A2, and so on, right? And each of them will receive a phase phi 1, phi 2, phi 3, and so on. And then there is the spacing, and this spacing could also be D1, D2, right? D3. So all these variables, and if you make this spacing equal, and and since they are arranged in one linear lines, in this case we are calling it a linear array because the elements are placed along one axis and the spacing is equal. But you could also have the spacing is unequal. You can have two elements very far apart and two very close, and you can rearrange, and all these will again affect the array factor, which affects the radiation pattern. They could have different amplitudes as well, or they could have the same amplitudes. They could have different phases, which is used in beam steering. So all these things you can actually do, and if you are able to make an array and with a circuit such that you can control all these variables, you can do a lot with that. You can keep changing patterns based on your requirement. So an array also the you need not have the same elements to form an array. You can also have a dipole and then do a monopole or something, and then have a slot. You can combine all these different elements and also create an array of different elements. Right. So the total field of an array is calculated by doing something called as pattern multiplication. So you multiply the element pattern with the array factor, and this gives you uh, 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 the pattern of the array. So let's say if your half wave dipole has a radiation pattern which looks like this. So I mean, if you make the complete pattern, it will look something like this, a donut cut from the vertically cut. And your array factor, if it looks something like this, if you draw it in the entire 360-degree angle, yeah, and if you so both of these will multiply, and then you get your final radiation pattern, which will look something like this. Since so you'll notice over here, since this is this is zero over close to zero over here, and this that had some value, but when these multiply, this became smaller. Similarly, this value into this value became a smaller value, but it had maximum value over here and it had maximum value over here, so it stayed maximum. So so these two are not exactly same. They look similar but not exactly same. And for example, if you had a pattern, let's say your element pattern was something like this, and your array uh, pattern was something like this. And if these two were multiplied, then you'll look at your pattern would look something like this, because it had a null in the center over here. You had a null over here. So in that case, although you had a maxima in the array factor, when they multiply, this will become zero at the center. But you had maxima somewhere here, so that will represent that will come over here. So essentially, this is we'll see more on this, and then you have your array factor derivation. You can I won't go into these because these are like summary, and then you must go through textbook to get how the array factor is derived. It's pretty straightforward, but I would recommend that you go through the textbook. We're just noting things over here. So the important thing is this phase term and then how the array factor equation looks like. And this is the general, these are the general expression. So these change with based on your antenna. So we won't be directly using this. I will be using some version of this. Now, what does a broadside mean? The broadside means being perpendicular to the array axis. So your array axis is the x-axis. Again, this is the x-axis, and your beam direction should be normal. So that becomes your broadside. That is your broadside direction. So this means your beam should be along z-axis. Your your beam should be along y-axis, and theta equal to 90. Yeah. So if this is zero, theta 0 over here, and in this direction, this becomes theta equal to 90. 90 over here. And then your beam condition is given as this. So you substitute the value, substitute 90 over here, and this gives you beta equal to 0. So now you have the value of beta equal to 0, and this broadside array will use 0 progressive phase. So beta essentially reflected the phase shifts over here. And since beta is 0, so all the elements will have the same phase. All of them will be at 0 excitation. Now, to implement in MATLAB, we're designing these arrays at 3 gigahertz. You can just change the F naught and the script, and this will can automatically adjust. And then your wavelength is C by F. Your spacing is lambda by 2. You must try varying the spacing. Try varying this spacing D. Okay, and also varying the number of elements. N is the number of elements. Over here, we have taken n equal to 8 and d equal to lambda by 2. Uh, Vary these and see what happens with the radiation pattern. And for a broadside condition, beta is equals to 0. So the script also reflects this. And then once you put this, we can use show and look at the pattern. But before that, the script that I have shared, it also includes some analytical calculations. So let me just go through that as well, so that you don't feel it does not feel unfamiliar, right? What the script says over there. So if you refer to the theory textbook, that will show you that the half-wave dipole has the radiation pattern of this. So this comes after a long derivation. So where you start by having a dipole, and then for the dipole, you calculate your vector potential, and from vector potential you get your uh, electric field. Electric field give you magnetic field, and from the electric field again, and from both these two, you get your pointing vector, and then pointing vector gives you radiation intensity, and then radiation intensity radiation intensity is represented by U, and then from there you get the radiation this element pattern. Element pattern is basically when you write the radiation intensity and then you uh, normalize it, that becomes your element pattern. So I won't go into this derivation. I already have the lectures on this. You can refer to the theory lectures on antenna, and so this is there. So once you do all this, you'll get the element pattern, which looks something like this, and you can plot this element pattern. So what this expression has, it has a theta variable which you have to sweep. So you define theta from 0 to 180 with the 0.5 spacing. Then since this is you have this in degree, then you convert it to radians. So you can use a degree to rad function from MATLAB. So you now have theta in radians. Put this as sine theta. So now this becomes you have defined the sine theta function, and this is your sine theta. And just to avoid any zero values while plotting, you can see there's some error happening here. This would be even worse if we did not include this. So we define the initial values. This is just a fail safe, not physics important. This is how you define the sine theta. So this sine theta you have, and similarly you can do it for cos theta as well. Because and we did this because we had sine theta in the denominator. If we don't do this, this will become a divide by zero error, and that will be a problem. So we do so we have cos over here, and pi by 2 multiplied by cos theta divided by sine theta, and then whole square. So this is your element pattern, and then we are normalizing it with the max of the element. So and when we plot this, okay, you have to convert this in dB. You can do that by using 20 log 10 and then your element. And you plot this, you'll get the element pattern looking like something like this. So if you notice, your maximum is at 90 degree and your nulls are at 180 and 0 degrees. Now, similarly for the array factor, your phase term looks something like this, your array factor looks something like this. And you can combine these and write like it like this in the script. So we use an absolute because we just want the magnitude over here, and then you have the summation running over here. So you have your summation, and then you have exponential. You to write this imagine number, we use 1j because using just j will uh, only j is a variable. So 1j MATLAB understands it as I or j for imaginary things. And then we are sum we because we are using a sum function, it should have a vector inside. So 0 to n minus 1, 0 to n minus 1 over here, and then we had uh, psi over here. So the psi is written as kd cos theta. So kd cos theta plus beta, and then you know 1 over here, and then this whole thing is squared. So I think I'm missing the correct expression over here, but you can refer to the script for this. This particular thing is uh, this script is correct. I think I'm missing the correct array factor formula over here, but it looks something like this. Okay, so once you define the array factor, you can again plot it like the element pattern, and then you can multiply these two, and you'll get the total pattern. And similarly, what happens if your element pattern changes? For example, for if you use a if you change the orientation of your dipole in that case, and if it looks like an isotropic pattern, and so it's again this two will multiply since its magnitude is one at all the angles. After multiplication, these two look similar. Now, let's see the effect of the number of elements before we do the MATLAB antenna toolbox simulations. So if you increase the number of elements, so you can modify the script a little bit just by increasing the number of the array elements. Run the script for 1 to n list, and now we have the n list as 2, 4, 8, 16. These are the different number of array elements that we want to plot, and we have put the plot function inside this loop itself, so it will generate all these plots. So if you keep increasing the number of elements, you will see your beam width becomes narrower, right? Your beams become narrower, and if you do a full EM simulation, you'll also see your gain will increase. So this plot is normalized. Uh, if you do not normalize it and do a full EM, you'll see your gain also increases. Now let's do a full wave validation using the antenna toolbox. So to define an array, what we do is we again we just call and we have decided that our array element are all the elements are dipoles. So what we do is we make a dipole. We use lambda by 2 length, width as lambda by 200, and then you by using the dipole class function, we are defining it as element 80. So this is a variable that we are creating the instance of the dipole, and then we want to create an array, and the array is a linear array. So you can use a conformal array from MATLAB. If you if you want to change the positions of individual elements, and if you want to use just a linear array, you can directly call a class for linear array that just simplifies everything. So it will automatically you can specify the element spacing, the number of elements, uh, and the phase shift, and this automatically fixes all these. You don't have to individually specify, and you can just uh, assign the array element as element 80 that you had you know needed over here, so you can define it over here. But if you want to mix different kinds of arrays, or do a different excitation for each of them, in that case you have to use conformal array. And then to show the geometry, once you have created the array, you will use show array, and this will just give us this plot over here. So this is how we create the array, a linear array with dipoles. And then once we have this, we can just you know do a pattern analysis. You can also do an S parameters, but that seems a bit pointless to do in an array for now. But you can because you to get the correct is parameter for the entire thing. You need to connect all these elements to one particular field, because an antenna array will have just one port. So you need an S11. But if you do an S parameter analysis of this will give you the interaction between these elements. So that's not right. So that becomes a different problem, a later problem. Right now, we'll just look at the pattern. What happens if all these elements are excited together? If we are able, let's just imagine that we have a feeding network connected to all these dipoles. So in that case, this is how the pattern would look like. So this is our expected broadside radiation happening. We have seen this plot before also, and if you we'll run this and see that it all maintains the symmetry, and gain also increases with respect to a single dipole. So the key takeaways from this particular simulation would be the broadside is achieved when beta is zero. So where that is when all the elements are excited in the same phase. We notice that the beam is perpendicular to the array axis. The beam width decreases with n, which we saw in when we varied n equal to 2, 4, 6, sorry, 2, 4, 8, and 16. 12. And then pattern multiplication was verified, and uh, from theory also we saw that if your element pattern looks something like this, your array pattern looks something like this. So our antenna pattern would also the array factor look like something like this. So our array pattern would also look something like this. And always remember, for a broadside array, all elements radiate in the phase perpendicular to the array axis. So it's all of them will have a phase perpendicular to the array axis, right? In that case, they all constructively add up in this direction. And for an end fire, they will constructively add in this direction. So let us run the script, the arrays, uh, the broadside array. I guess everybody has the script with them. Yeah. So if you run this script, let us just quickly check the script again. So this is the script everybody has. So we are doing broadside array. Like previous scripts, we set up the plots, axis, and things, and then we define the usual parameters. And then for array, we define these new parameters: the number of elements, the spacing, and the broadside phase, which is 0. And then we define for the analytical calculation, we define theta, and then theta in radians, and then sine theta, and then make sure that our denominator does not go to 0. And then write the element pattern of dipole, and then plot that. Similarly, the script also has two different configurations where you can have different, isotropic pattern, or a dumbbell shape, or a balloon shape. So you can comment and comment and check different element patterns, and when they multiply with the array factor. So the expression for the array factor is over here. And then you plot it in dB, we change it to dB. And then how do we get the total pattern? We just multiply the element pattern and array factor, and you get the total pattern. And then again, you convert it to dB and to plot it. And here is how we are plotting it. Subplot 1, 2, 3 for the element pattern, the array factor pattern, and the total pattern. And then we study the effect of number of elements. So we just create a list of the number of elements that you want to study. And then based on this list, we keep changing the array factor. The element pattern remains the same. And so we're just plotting the effect of the array factor over here. So uh, we, we calculate the array factor, and then we plot it. And then we do this inside the loop, and hold on, make sure that your figure stays active, and then on the same plot it plots again and again. Okay, and then you put hold off, so that no when we need no further plotting on the same figure window. And then you add x labels and y labels, and then you do a full wave evaluation. So let me first show you these plots. So if you're using a recent version of MATLAB, you actually docks all the figures together. So this is your pattern multiplication plot that we saw. If the element pattern looks something like this, your R factor is this, and so it multiplies to show this. Your effect of number of elements, uh, your beam width becomes narrower as you keep increasing the number of elements. Okay, so we have discussed these two. You can also tile these plots so that you can see all of them together. Let's come back to the script. So the script, now we are starting with the full wave validation using the antenna toolbox. So first we create the dipole element. We create a linear array. And then the for the linear array, the element is defined as your dipole element. And then we define the number of elements, the element spacing, and the phase shift. Then we use show array to show the geometry. So if you use the geometry is shown over here, and then if you use pattern function, it will show you the pattern. And then you can also use azimuth pattern and elevation pattern to get plotted either in coordinate or in polar coordinates. So these two are essentially the same figures, but in different coordinate systems. So let me just quickly run through the script as well. So for 2D patterns, you save the pattern values, normalize it. For HPN also, you save the pattern values, normalize it, and then use for the Cartesian coordinates, you just use plot. And if you for the polar plots, we just use polar plot over here, and then it shows, and then you choose uh, the same values, the E plane and H plane that you calculated. You can use these variables. This is for the normalizing this, and then just changing the line width. We come back to the screen, and pause here so that you can look at the results. And I hope you guys have the scripts with you. And if you want to run it now, I can run it. And if there are issues or doubts that you want to ask, you can ask now. So I'll pause here for maybe a minute, so if you can run the script and see for yourself. And then we'll move to the end fire uh, antenna array. Okay. So if you, I hope you guys have had enough time to run the script. The simulation does not take very long, and the script should be working fine. One important announcement that I forgot to make in the beginning of the class was I'll be sharing the feedback form maybe today or tomorrow before the last class, and I would expect everybody to fill up the feedback form within like a day. I'll give you another one more day after the last class, and after that I'll close the feedback form quickly. So I won't keep it open because I do need to finish this class, all the logistics around it, and I'll have to share the feedback form with the organizers. So please make sure you fill up the feedback form, and that is important. Why? Because if you want a participation certificate, uh, only the people who have filled up the feedback form will get a participation certificate. So mm, if you if you had not registered for the course, that's fine. If you're in the WhatsApp group and you have the access and you have filled up the feedback form, uh, that is enough for you to get the participation certificate. But if you don't fill up the feedback form, I won't be able to give you a participation certificate. And if you don't need a participation certificate, you are here just to just learn and enjoy the class. So that's up to you. But the feedback form is a must. And you can also give me feedback because I go through them and I try to improve on my lectures. That's about. I also write about this in the WhatsApp group, so that should be okay. Okay, coming back to the end fire array. So I've already completed the broadside antenna array. Now coming to end fire array, and the end fire array is just the opposite of the broadside array. Again, even if we arrange it in the like so, so the array elements and the array has the same orientation. But what happens is if you change the phase of each element, you can actually steer the beam. So in a broadside, it was normal to this. It was radiating in the normal direction to the array axis. but in the end fire, it radiates towards the ends in the other direction. So the array actually, if you look inside this pattern, it's arranged on the x-axis, and the radiation maximum is in this direction. Okay, I think I forgot to show the broadside array plot by rotating it. So let me just unlock this pattern. Yeah. So make sure you take a look at the how this dipole array is moving along with this radiation pattern. So if I try to rotate this, you'll see this is the top view, and this is the top view. If you notice, the array is in this direction and the radiation is maximum in this direction. It is normal to the array axis, right? So the radiation from each element acts constructively normal to the axis, and we get the nulls on the along the axis. Now, I think it's best if we run the entire array code first and then get back to the slides so that we can see the contrast. So I'll run the entire array script. Uh, if you guys also have the script with you, so you maybe try running that. Yeah. So these are the ENH plane cuts. This is the effect of the number of elements. We'll look at this later. We'll look at the pattern multiplication also. So these are the results it is generating. We'll only focus on this result now. See, compared to the broadside array, we see the radiation is maximum in the along the axis, and it is we have a null actually in the forward direction. Right. So in the broadside direction, we have a null, and we have the radiation maximum in the direction of the array. So this is the important characteristic. And so, and the only thing that we changed was the excitation of each of these elements. We did not do any modification in the physical geometry. So, and this naturally leads us to think one particular phase, like that is zero. If all of them have the same excitation, the radiation is in the broadside direction, and for a different phase the radiation moves towards the axis of the array. So there must be other phases which would tilt the beam in a desired direction, so which leads to the concept of phased arrays. Okay, so we'll go back to the slides and then go through and look at how the end fire array script is written. Meanwhile, you can also try to run the script in your PC and see if you get the similar results. So previously we had beta equals to 0, which ensured that the radiation was in the broadside direction. But now yeah, that is perpendicular to the axis. So this is the array axis, and the radiation was perpendicular. Now what if we wanted beam along the array axis? So one of the ways is you can just physically change the array dimensions, and you can achieve that. But if we have the same structure and we have the flexibility of changing, and that would result in radiation in this direction, and this is called an end fire array, and the name is pretty self-explanatory. It is firing from the end. And just to compare, like this is from the textbook. You can check PA Balanis. Antenna theory by C. Balanis. We'll get this figure. So this is the broadside type of array, and this is the end fire type of array. And you must notice the broadside array actually has a narrower beam width for the same number of elements, while the end fire has a much broader beam width. But this is still better than just a simple dipole, right? And then you can, and this is from the textbook. The general phase term looks like this. And to radiate around along 0 degree, the beam condition becomes this. So this has to be zero. This implies sine theta. And since sine theta is 0 degree, this implies KD should be equal to negative beta. Beta is equal to minus KD. And so this is our condition for end fire array. So this implies all the elements should radiate in phase at 90 degree. So, sorry, in broadside, they all of them radiate at 90 degree. In end fire, we have to delay each element progressively. So each element has to delay its radiation so that it adds up in this direction. We have higher gain over here and a null somewhere here. And this progressive phase is beta equals minus KD. And if you calculate the value of beta, your d and your since our element spacing is lambda by 2, and k is the wave number, which is 2 pi by lambda. We multiply this ends up as beta is equals to minus 5. So we get that each element should be shifted by minus 180 degree relative to the previous. So if the first element is at 0 degree phase excitation, the next one should be minus 180 degrees. And then the other one should be minus 360 degrees, which is essentially 0 degree, and so on. Right. So in the script, we again initialize parameters like this, and then beta is defined for end fire as minus k times d, and then the array factor. Yeah. So the previous expression, the array factor was missing. So this is the correct one. The array factor is expressed like this. So this is just the written version of we are writing this expression in MATLAB like this and normalizing it. And then this is to get the log values. So the array factor for an end fire looks something like this. So we now your broad side had an array factor pattern something like this, right? The red one, and the blue one is now your end fire. So it is radiating towards the ends. So the end fire, so the element pattern, if looks like isotropic, and then your array factor uh, something like this. And so if you multiply these two, you will end up with the total pattern something like this, where we have maximum radiation at 0 and 180 degrees, and your array is actually arranged in along this line. So you have maximum radiation towards the ends. So similar to the broadside array, we have also the script for the end fire array also has some parts which will do theoretical calculation to show pattern multiplication. And similarly, once you have written the element pattern and array factor, you can get the total pattern like this and normalize it and then plot this. And like the effect of number of elements in broadside arrays, we can also keep increasing the number of elements in and keep the phases suitable for end fire array. And you'll see that the in this case also the beam becomes narrower. You keep increasing the number of elements, but you have to notice that the end fire beams are typically broader than broadside for the same end. So, for example, if you get like 15-degree beam width for let's say 8 elements, uh, it will be like 25-degree or something for 8 elements in end fire case, right? So broadside will have a narrower beam width, which is better. Now, the script is shown here is the same thing. If you want to study the number of effect of elements, it's the same script which we use for broadside. It's just that your array factor is and your beta is changing over here. So beta is equals to minus KD, and we keep increasing it over, and this you'll get it. And so to do a full wave, again, we use the same element, same linear array, same number of we use element array, same element, same number of elements, and same spacing. But array phase shift, this changes to this function. Now we're just changing degree to radians over here because array phase shift takes arguments as radians. So let's ignore this. This is just changing degree to radian. Now, what we are doing is we're changing phases from 0 to n minus 1. We have n elements, so we're starting with 0th element to n minus 1th element, so n elements, and we're multiplying it with beta. And what this does is this creates a progressive phase shift within the array elements. So this is how you do it in MATLAB Antenna Toolbox. So while using linear array, so this we have now created phase shift for each of these elements, and once this is done, we have actually created the antenna array. Now we can just use the pattern function and look at this pattern. So it's the same linear array, different phase shifts results into a different radiation pattern for the entire array. Now, comparing broadside versus end fire. So the broadside beta is 0 and fire is minus KD. Your beam direction is 90-degree in broadside, it's 0-degree in end fire. Radiation is perpendicular to the array, this is along the array. Gain is higher in broadside because you have a narrower beam, so more power is concentrated in the narrower beam. And this is slightly lower than the broadside, but this is also very high. And then the beam width is narrower as compared to end fire in case of broadside. So I'll pause over here. I'll just conclude with this slide and then pause over here. And then if there are questions, we can discuss. Else, we have a few more slides covering the phased arrays after this. So the end fire is, to summarize, the end fire is achieved at beta equal to minus KD condition. Beam is along the array axis. Pattern multiplication, we again verified this, that pattern multiplication is correct. And we verified it with theory. If you just check out the script, and the phase progression steers the beam. So this is the most important summary. The phase progression is steering the beam. So when there was the zero phases were there, they were radiating in the normal direction. But then when we changed the phase, it started to radiate towards the other direction. So this implies if we tune the if we keep changing beta, this will keep tilting the beam in different directions. So this naturally leads us to phased arrays. I'll pause over here. I'll show you the different results which we got from the end fire array, and if there are questions on that. So these are the results that we achieved from the end fire array. This is the pattern multiplication, the effect of n. Sorry, this. This is your 3D radiation pattern. And then you can also look at the ENH plane cuts. So these are the different results that we generated. So this is the most important one. And then you can also try to rotate and see how the pattern looks like. So it is definitely radiating in the direction of the array. So now we'll look at phased array. Based on the discussions from broadside array and fire array, we have a natural intuition that changing the value of beta helps us steer the phase. So we'll just look at that. And the example that we'll be doing is the example we'll be tilting the phase, sorry, tilting the beam to 30 degrees. And this is the goal. This is what we'll achieve. So we have the same array orientation, same dipoles in the x-axis, and they are oriented in the z-axis. So all the dipoles in the z-axis, and they're lined up in the x-axis, and all of them still have the same spacing as lambda by 2 and the same amplitude there. They have the excitation. The only thing that will be changing is the individual phases of these, and we have to find out the correct value of beta to get 30-degree shift, 30-degree tilt. Now, broadside had beta equal to 0 and fire had beta equal to minus kd. So the question for this in the coming slides is that can we point the beam at an arbitrary angle? And the answer is yes. And this is called phased array steering. So a lot of you must be already familiar with phased array steering, but we'll see how to do that in MATLAB. And the important thing is to note that the geometry does not change. So we're not changing this, but we're just changing the phase, and that leads us to a 30-degree tilt in the radiation pattern in the beam. So now we want to tilt the beam, and to do this, we have to we must note that broadside had this broadside is elevation at 90-degree and far is elevation 0-degree, and we are tilting the beam 30-degree from the broadside. So the array, if it is arranged like this in along this axis, and this is your 90-degree, and this is your 0-degree, and we want to tilt the beam, and we're tilting this from the broadside because that at the broadside we have the max radiation, right? We have the max radiation, and so we are tilting from the broadside, the 30. So this is 30 degrees. So this implies that from the zero axis, this will be 60-degree naturally. So the elevation is now 60 degrees. Now, using the phase term in the E-plane, we had the psi is equals to kd cos elevation into beta. Now, for maximum radiation at this elevation angle, if we can solve this, this implies beta is equals to minus kd cos the elevation angle. So this becomes the universal steering formula. And now we can substitute this value and try to simulate. Now we have given elevation as 60-degree, and then beta becomes this particular value. Now cos 60-degree is 0.5. This implies beta is equals to minus kd by 2. So this is what the code will compute. The tilt is defined from the broadside, and uh, L naught is the MATLAB elevation. We'll see in this script, and beta is directly computed from the steering law. So this the steering law is this particular expression. So we'll just in MATLAB code we'll just keep changing the value of this L naught, and beta will automatically get calculated. And when beta is automatically calculated, the array factor and everything gets automatically calculated. So once you run the script, you'll see the theoretical array factor, which is in blue, and the simulated one, which from the full wave simulation, they match pretty well. And if you notice, this beam steering is happening at 30-degree from the broadside. So don't get confused with these the this orientation of this plot. So this is actually so this is your arrays arranged in this way, and your beam tilt is 30 degrees from the broadside. Now, for the MATLAB, this remains same. This is defining the parameter. Now to steer it, for the steering, we define a variable called as tilt as 30-degree, elevation as 90 minus tilt, and then we define beta with cos d L naught. And so this cos d is basic. So cos in MATLAB takes input as radians. and cos d takes degrees, right? So hence we're using cos d over here. This is just another function so that you can input angles in degrees. So this is for steering. And then we again substitute beta value is equals to KD. You have to do like to get the array factor. But again, this is not important because the code directly substitutes the beta value inside this, right? So the array factor expression remains same. We're just taken out the psi value, and the psi is this whole function over here, and then beta is automatically calculated. So this is just to show you that beta is minus KD by 2, but it is automatically calculated in the script. And then you can create, so this is for the theoretical calculation. So again, this does it, we don't have to even care if we are just doing an EM simulation using the toolbox. So in the toolbox, what you do, we just create an element. We create an array of linear. The element is dipole. Array is linear type. We assign the element as LM, which is the dipole. The number of elements as N. Spacing is D, and we create the phase shift as right to degree and beta. So we're just giving beta over here, and the beta is again calculated using your L naught, right? So if you remember, we just calculated beta with L naught, and then given this as phase shift to this function over here. Then simply we just write pattern, and this will give us this particular result over here. And so let us first run the script and see the results, and then we'll discuss a little more and finish up with this class. So looking at the phase, so everybody must have this phased array MATLAB script. So let us run this. So if you run the script, all the results, the figure will get plotted. Let me just change the layout. Yeah, so this is all the results that will happen. So the script first calculates the normalized array factor using theoretical calculations, and this also detects where the beam is. So it will automatically put a marker which is calculating the maximum value in this array, which is your normalized array factor, and the your beam is somewhere close to this will show 60 over here, which is essentially 30 degrees away from the or broad side. And this is your theoretical array factor. And similarly, this is your 3D radiation pattern from the pattern function. And then if you take a E-plane cut of this particular radiation pattern, you will get this. And this again matches your theoretical array factor. So these are in Cartesian coordinates. You can also plot them in polar coordinates, overlay them, and see this is both of them are at 30 degrees. And then you can also simulate, most plot the simulated E-plane and H-plane of this particular 3D pattern that we've achieved. Now let us look at this properly. So this is the 3D radiation pattern. Again, we have the same array. For 0 degree phase, it was broadside. For beta for minus pi, it was end fire, and for 30 beta equal to some 30 degrees. For 30 degrees, it will calculate beta value, and this is how the radiation pattern looks like. See, when all the arrays are lined up along the axis, the beam is tilting 30 degree uh, from the broad side and 60 degree from the elevation. Right. So this is the radiation pattern, and this is only steering in one direction. And similarly, you can scan through the entire this region. So as an assignment, I will leave it up to you to change different beta value. Different plot the radiation pattern for different beam steering angles. So this is all the results. Looking at the script, it will, if you have seen the end fire and broadside array script, this will seem very familiar. We have the We have the we have the regular parameters, the array parameters. Now we have included these three variables: tilt, L naught, and beta. Beta was already there. Now beta is calculated from L naught. We just print these values, and then again for theoretical calculation, we define elevation convention. The psi value is essentially, the argument inside the array factor, e power j some psi. So this is psi. We have written this outside. You can directly write it inside also. Then find out the array factor, normalize it, write it in dB, find out where the maximum array factor value is, and you can plot that. For full wave, again, we define the element, define array element, number of elements, element spacing, phase shift. Phase shift is basically this takes value in radian, so we convert from so so this takes in degree, radian to degree. We are converting it, and then the beta value, and then just to get the pattern, we just use the pattern function like earlier, and then E plane, H plane, and all these just different functions to plot uh, polar plots and your pattern functions, 2D cuts. So the script is pretty much straightforward, and you get your phased array. I'll pause here and let you run the script and get this result. If there are any problems, we can discuss. And just to summarize, we had the beam direction is controlled by the phase. The beam direction is controlled by the phase. The spacing controls the grating lobe. So you do try to vary the spacing between the array elements. Also try to check, try to change the value of the amplitude and the phase progression between. So try different beta values. And this is the steering law. And for broadside and end fire, now once you have looked at the phased array, the broadside and end fire, they become special cases of the phased array where one is radiating perpendicular to the array, and one is radiating in the direction of the array. So that's it for today. If there are questions, we can discuss them now. Else, we can conclude today's class. Uh, so there are no questions. We'll end today's class. You can go through the slides I've already shared. You can go through the script, run them for the horn, the patch, and the three array cases, and get back to me in the WhatsApp group. That if there are any questions on this, you can and definitely try to tweak the code and see what happens. And the So can we get this? Yes. So I'm sharing all the presentations and everything uh, in the WhatsApp group. Hamid, are you there in the WhatsApp group? If not, please join. I'll share the link with you. Um, Let me check. Yeah, I'm sharing the uh, link in the Teams chat now, just in case if you are not there already. So this is the link to the WhatsApp group. I've shared material there. Now that you say that you don't have it, I'll share this again. Right? Um, any more queries on this? I'll, okay. Okay, Ahmed, you're here. So this lecture was already provided. So I'll put a dot on the lecture. Just refer to the previous the charts at 3:22 a.m. The message is sent by me. It has all the scripts and the lecture material there. So there is no slide for horn antenna though. It's just the script. Okay, if there are no more queries, questions on this, thank you guys for joining. And especially because this was a Sunday and everybody needs a day off. Thank you for joining on the weekend. The next class, I have one more class to cover. If I'll try to do it within the week actually, so that we wrap up during this week. Um, yeah, but I'm sure I won't keep it on holy. That I'll ensure. If not, we'll definitely finish it on Saturday. Okay, guys. Thank you for joining. I'll stop the recording now.